Okay, we're now ready in this particular chapter to look at a special case involving a mixture of two gases that we'll be treating as ideal gases. And this particular mixture is the mixture of air, what we will refer to as dry air, with water vapor. Now, in this particular case, the air that we're using, we're going to assume is a single gas. We know that air really is a mixture, but we can represent it as a single gas with various properties, molecular weight, and other things like that. So in this particular case, we're looking at a mixture of these two components, dry air and water vapor. And when we have water vapor, H2O, as in the vapor phase, we then call that moist air. And again, the dry air component is considered a pure substance, as is the water vapor. And so if we have that mixture in a container that occupies a given volume, and if that mixture is at a mixture pressure P and at a temperature, a mixture temperature T, we then can say that the ideal gas equation holds for that mixture, and it also holds for the two components like we've seen before. We're going to assume that the air, the dry air, consists of N moles. That is a mass of Ma. We're going to assume that the water vapor consists of NV moles along with MV mass. And then our mixture itself is the combination of all the moles to be little n, and the mass is the total mixture mass, which is capital M. And so, as I said, we can now write the ideal gas law for the mixture pressure, the mixture temperature, the total volume, and the total number of moles, written here with the universal gas constant. We recognize that the total number of moles can be written as the total mass, where we bring in the molecular weight. And so with the universal gas constant divided by the molecular weight, we know that that's the specific gas constant for air. And so this is the form of the ideal gas law. We can also write the partial pressures, the pressure associated with the dry air, based on the overall volume, the mixture temperature, and the number of moles of the air. And we see that we have that, and we can also write it in terms of the mass of the air and the molecular weight of the air. And we can do the same thing for the partial pressure of the vapor, which is the water, in terms of the number of moles of the vapor, the temperature of the mixture, the total volume, and again we can write that in terms of the mass of the vapor in that mixture. We recognize that this partial pressure of air is simply the mole fraction of the air times the mixture pressure, and the partial pressure of the vapor is equal to the mole fraction of the vapor times the pressure of the mixture. And so this is our moist air and how we can represent the pressure, volume, temperature relationships. So now we are interested in introducing what is referred to as psychometric principles. And basically, psychometric applications are those applications wherein we're dealing with moist air. The first term that we need to introduce is what is referred to as saturated air. And what saturated air is when the partial pressure of the water vapor is actually the saturation pressure at the mixture temperature. Okay, so let's define this concept. What I have drawn on the screen here is a temperature volume dome associated with water vapor. Okay, now this is just the pure substance water. And what we know is that there are lines of constant pressure that can be drawn on such a curve. Okay, prior to this time, we looked at pressure volume, and we talked about lines of constant temperature, but now we're interested in the temperature volume, and we have corresponding lines of constant pressure. We know that these lines come up in the subcooled region, they go across at a constant temperature, and then they go up into the superheated region. And so if the partial pressure of the vapor happens to be at the saturation temperature associated with that partial pressure of the vapor, we have the state of the vapor is right at the edge of the dome. Because we know that this pressure is related to this temperature. Now, if the partial pressure of the vapor is lower, it then, as at the same mixture temperature, it's then out in the superheated region. And so if we are away from the dome at that particular temperature at a pressure that's lower than the saturation pressure, we see that it is a substance that is out in the superheated region. And so when we say we have saturated air means that the air is got as much vapor as it can hold, and that corresponds to a pressure corresponding to the saturated condition at that mixture temperature. And so anything less, we still have a moist air mixture, but the air itself could actually hold more water than what it is actually holding. How much, or how do we define how much water is in the mixture when the water is over in this region? We do that with a couple of terms. The first term is one that's referred to as the humidity ratio. And the definition of the humidity ratio is the ratio of the mass of the water vapor to the mass of the dry air. And so it's given the designation omega. And omega, again, is defined as the mass of the water vapor over the mass of the dry air. If we were to substitute the ideal gas law for the mass of the vapor, we see that we can use that equation here, basically solving for mv. And when we do that, we have the numerator. Likewise, the air behaves as an ideal gas, and we can write that utilizing this equation here for Ma. And then we put that into the denominator. And for this mixture, we recognize that the volumes are the same, the RTs are the same, and so what remains then is the molecular weight of the vapor times the partial pressure of the vapor, the molecular weight of the air times the partial pressure of the air. And so, since the vapor is water, which has a molecular weight of 18, and air is a pure substance assumed to have a molecular weight of about 29, 18 over 29 is 0.622. And so 0.622 is this ratio. Pressure volume is in the numerator, and then the pressure of the air is written as the mixture pressure minus the partial pressure of the vapor. And so this PA, we know that PA plus PV is equal to P, the mixture pressure, and so we decided just to write it in terms of the mixture pressure and then the partial pressure of the vapor. And so this humidity ratio is a number. It's a non-dimensional number. It's mass over mass. It can be in pounds over pounds. It can be in kilograms over kilograms. It can be in grams over grams, but it is a non-dimensional number, and it represents how much water vapor is there in the mixture. If the partial pressure of the water vapor is 0, which means that there is no moisture because there's no partial pressure, we see that the partial pressure, the humidity ratio becomes 0. Another way of defining this, how much water do we have, is something called the relative humidity. And what the relative humidity is given by the designation phi, not to be mistaken for an exergy, but it is the relative humidity, and it's the ratio of the mole fraction of water vapor to the mole fraction of a saturated mixture at the mixture temperature and pressure. And so the best way to think of it is this second term here. This relative humidity is the magnitude of what the partial pressure of the vapor is divided by the actual saturation temperature associated with a mixture that was at a temperature and pressure. So it's best to look at that on this curve right here. If we had a given mixture temperature and a given mixture pressure, and we had a certain amount of water that put the water pressure, partial pressure here, and if we were to add water to the mixture, holding the same amount of air, dry air, and holding the same total pressure and the same mixture temperature, whenever we approach this value of the saturation pressure for that mixture temperature and pressure, that then is a fully saturated dry air, and that would correspond to 100% relative humidity. As we move away, it's less and less relative humidity. And so the ratio of the magnitude of this number over this number is always higher than this number because that's how the pressure lines are. But as this number approaches the dome, we see that we go to a state of 100% relative humidity. And again, it's related to also as the mole fraction of the vapor over what the mole fraction of the vapor would be if we were fully at the saturated condition. And so two very important terms, a relative humidity and a humidity ratio and a relative humidity value. And they tell us basically how much water is the dry air holding. Okay, now that we know that, we now have to ask ourselves, what are the thermodynamic properties? How do we determine for those conditions what the mixture enthalpy is? And so it turns out that the mixture enthalpy for a mixture of dry air and moisture is given as the total enthalpy, capital H, that's for the entire mixture, but it's relative or it's referenced by the amount of dry air. So we've typically not looked at properties like this. It's a specific property because it's based on a per mass, but it's the total enthalpy of the mixture divided by the mass of only the air component. And so that then turns out to be equal to the specific enthalpy of the air only, which is this term. And so that would be how much energy per mass of dry air. But then we have this term here, which is once we have the specific enthalpy of the vapor, we then multiply it by the mass of the vapor over the mass of dry air. And what happens when we do this is that this enthalpy is on a per mass of vapor. And so when we multiply the mass of vapor over the energy per mass of vapor, we just get the energy of the vapor component, but then we divide it by the mass of the dry air to put it into the same units as this left-hand side. And so that term there becomes omega, our humidity ratio. And so now we say that the enthalpy for the mixture is given by the enthalpy of the air component and the enthalpy of the vapor component multiplied by the relative humidity, or the humidity ratio. Now, one of the assumptions that we'll typically make is that when we are trying to determine the enthalpy of the vapor, we recognize that it's close to the dome, and we're going to make the assumption that anytime we're close to the dome, we're going to assume that enthalpy is just equal to the enthalpy of the saturated condition at that particular temperature. And so in essence, it's saying that if we were here at this point, the enthalpy associated with this point for the vapor can be assumed to be equal to the enthalpy that one would have if one came across at the same temperature and ran into the dome at that particular point. And that's not a bad assumption. It's basically saying because it is an ideal gas, that the pressure doesn't have as strong an effect as we typically have. Usually when we are close to an ideal gas behavior, the enthalpy is only a function of temperature. And so no matter where we are on this constant temperature line, we're assuming the enthalpy is the same. And we know the enthalpy at this particular point because it is the one of the endpoints associated with the saturation process. Likewise, if we're interested in the entropy for the saturated vapor, or for the vapor somewhere off of the side of the dome, we know that it is a function of temperature and the pressure itself. And so we can also, it also can be shown that that can be written as the saturation entropy associated with the temperature, and then this term here, which is a correction based on the change in pressure, because this is really the change in pressure. This is our relationship for how entropy is a function of temperature as well as pressure. The most important thing to note here is that we've introduced a enthalpy on the left-hand side here that is on a per mass of dry air. And we have typically not done that for a mixture. Okay, usually a mixture is the enthalpy on a per mass of the total of the mixture, but we've decided to only reference it with respect to the dry air component. And the reason that we do that is because the dry air component in most of our psychometric applications stays constant. Okay, and we'll see that in a second. Okay, when we come back, we're going to be talking some more about moist air, modeling moist air, and discussing equilibrium conditions, and eventually presenting what is referred to as the psychometric chart to allow us to determine the thermodynamic properties associated with moist air mixtures.